And that's what's been a big challenge for me is that, I go back and try to look back in the history, and it's really hard to understand what was really going on in say, Richard Sutton's head. Because I don't know him. I feel like I've met everyone but him. So there's so much I'd like to learn about the initial intuition, because these algorithms were cooked up without a lot of the same kind of motivation you'd get in a control course, where you're trying to say, I want to design this closed loop so that the eigenvalues of something are blah, blah, blah. Here it was maybe more speculative. And then it turned into something where you could create a scientific foundation. And so with that, let's get started with part two. And part two, click. And so, that's what's funny. The title really is part two is Q learning design. And so here again, wait, open this up. So I'm going to, present a history and my thoughts on the theory in a very, I mean, in a way that might be very distorted. I've been working this area since the 90s. When Ben Van was writing his dissertation, I was in contact with him because he had all sorts of questions about Markov chains and stuff. And then I had my first sabbatical with Borkar in the 90s and learned all about Q learning there with him. We wrote that influential paper. So I'm sort of trapped in the MIT school, which is completely a different perspective than somebody who grew up in the Bartow and Sutton school. And so excuse me if I make some mistakes in the history and stuff like that. But anyway, I think for this, I'm pretty solid, in terms of the history and who did what. When it comes to actor-critic methods, I still am not clear on who did what. And I'll talk about that tomorrow, who introduced what and when. So we've got, how control theories relate to Q learning. For some of you, that's obvious. For some of you, not at all. I'll go through it slowly. I'll talk about ZAP in that context, discussing the tabular case where it's really easy to see things, where this thing is really easy to compute. You can write it down. And I forgot I had this. So I mentioned during discussion that, you could cook up variations of ZAP Q learning that don't involve a matrix inverse. And I'll describe one version of that here. So far, the theory is perfect, but empirically it sucks. So I think there's a lot of work to be done there. I forgot I had that in there. We might not have time to go through it. We'll see how it goes. All right. Yeah. So in terms of resources, chapter 3 is all deterministic, but I really, if you're not an expert in this stuff, it's really a good idea to look at the deterministic theory first. Chapter 5 is deterministic again. Chapters 9 and 10 are both on temporal difference methods. Chapter 9 is really basic, going through basically ODE method for designing and analyzing TD learning, SARSA, Q learning, and all sorts of variations. Chapter 10 is more heavy duty because to explain, how you can get an unbiased gradient with actor-critic methods requires some heavy machinery, I think all from MIT, from the thesis of Konda and Ben Van and Marbach, all students of Johnson Tsoukalos. So I hope that Johnson Tsoukalos gets the next Turing Prize. I hear it's such amazing work in computer science. And then there's been a lot of new stuff. So when I wrote the book, I thought there would never be any hope on saying anything about the existence of a solution to what's called the projected Bellman equation, something I'll define in a moment. There it is. In the context of Q learning, that's called the projected Bellman equation. And so I resolved that recently. The paper just came out last year. But it's not true. We have counterexamples. So it's just that if you do the right exploration with Q learning, you get stability. That's what's really exciting to me. The fact, because let me tell you, when I first learned about exploration, all that, I heard people were so involved in that. I thought that they were trying to be greedy because they were trying to control a system online, and they wanted to apply the current policy because they're trying to learn to drive a car and drive it at the same time. And I thought you guys are idiots. And I wasn't at all interested in exploration. And then Ben Van Orr explained to me, no, 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 we're doing exploration because it leads to efficiency, you know, because basically, why would you try every state action pair over and over and over again when you've learned that some state action pairs are just are incompatible? And I said, oh, okay, then it makes sense. So then in my mind, it's all about efficiency. But now it turns out it stabilizes. So if you explore right, it stabilizes. So that's a new result, which is quite exciting. Now, there's relative Q-learning, and there's something called the advantage function, which are in the book, but very briefly done. I'm going to talk about that. And there's one paper there. This is just some methods to try to reduce variance and improve the dynamics. I mean, in this matrix, which turns out to be so important, is almost singular in Q-learning if you just run Watkins' algorithm, you know, and get with discount factor close to 1. One way to fix that is through either relative Q-learning or using what's called the advantage function. All right. And let me get rid of this. All right. So this is a joke picture from one of Carl Astrom's talks. By the way, I mean, this is an important picture in a way, in the sense that discussions that I've had with some of you today, you know, all of this field of RL is obsessed with optimization. We have an objective function. Once we've optimized it, we've solved a problem, we go home and we're happy. Well, that point of view kills people, you know. You know, it's really, I mean, if you're from a control background, you know that you can come with an optimal control solution and find out it's so sensitive, it's worthless. It's a meaningless solution. And so it's really good to keep that in mind, that optimal, why is optimal control such a big deal? It's a methodology to get a control solution. We never cared about that optimization problem in the first place. Now, there are counterexamples. In advertising, they want to make as much money as possible. There's one objective. If it destroys the environment, who cares? You know, no matter what, who cares, who cares, who cares? We're trying to maximize profit. And if it's non-robust, who cares? Maybe I'll get more money if the world blows up. In any other control problem I can think of, there's multi objectives, and one of probably robustness is more important than anything, you know. So RL is currently flawed as hell. Let's put that in the open problem sections, you know. Ideally, we'd have something as elegant as linear control, where robustness is directly addressed, you know. That's my dream. Okay, now I'll get off my high horse and go through the current theory. So first, deterministically, and this is partly just to give you some insight of what can be difficult. So this is this famous example of Fritz Sutton. It's for the book of Barnard Sutton. You're basically trying to get a car up to the top of the hill, and there's some physical laws here, and basically if theta of z, I guess, is the angle of the road, you get this differential equation for the position of the car. So you've got velocity as derivative position, and position evolves like this. We end up with a state space model. And the objective is to get there to the top of the hill as fast as you can. Now the problem here is it's a constrained input. So you can hit the gas full speed, you can take off your foot, but you've got a constrained input. And that's what makes this kind of tricky. And it's almost identical to the inverted pendulum, where you can just tap it back and forth, and you want to get and be stable up top. So it's very different regimes. This sort of swinging back and forth for a while, and eventually get to the top, and just a linear compensator will keep you stabilized at the top. So this is almost identical. And again, we want to reach the top at minimum time, and so we've got some value function, which is a function of the initial state. And so that's one step in all this. You have to choose a state. And in this case, position and velocity is sufficient. Often in RL, we don't have a model of anything, and we just grab a bunch of features and call it a state and go from there. And often it works. It's an absolute beautiful miracle that, that actually is, it's often so successful. Now, here's what I really wanted to point out is if you actually solve this problem, I think value iteration and policy iteration, they were covered on Monday, right? So those of you who were there. But anyway, you can solve an optimal control problem like that using policy iteration, value iteration. And this is showing how quickly policy iteration converges, even though, and this is discretized, we can't, the continuous time problems, the continuous space problem is, I don't know how to solve that, but once you quantize and approximate, you can use value iteration. And even though there's maybe, I don't know, a few thousand state action pairs or state input pairs, policy iteration converges in 12 steps, gets it exactly. Value iteration, after 40 steps, you're really there. But here's the issue that you really should keep in mind. Look at this monster. It looks like the Great Wall of China, sort of. It's a beautiful thing, this value function. Oh, by the way, this is, here I'm minimizing cost, not maximizing reward. I apologize to you all, but I'm from the control background. I minimize cost. I don't maximize reward. So this is a value function. And what's going on here is that the cheap states here are where I can basically hit the gas and get to the top. The control solution is trivial. Hit the gas, go to the top. This discontinuity is, just over here. If I just hit the gas, I would just barely make it to the top, and then I'd be stuck if I didn't let off the gas and roll back down. And that's where the inverted pendulum thing is going. So you've got this discontinuity. Can you imagine trying to approximate this with a linear basis? Can you imagine? I mean, what on earth would you choose? I mean, you could, of course, use binning, and then you could take every one of those little rectangles and have this incredibly high dimensional thing. But even a neural network, and the fact that a neural network works, considering, these smooth sigmoidal things, if you use leaky ReLU or whatever, you can imagine compositions of leaky ReLU can give you steeper and steeper slopes. But it's a nasty problem, even though it's trivial, And you can come up with ad hoc solutions to this. It's really easy to come up with parameterized families of policies that are you expect to be stable. But it's a cool example. So a really common approach to design is to propose a value function, even though you know it's wrong. You just come up with some kooky function, V. In the book, I give an example where you take it to be total energy, potential plus kinetic energy. I stole that from a paper on the inverted pendulum by Carl Estem and Mark Spong. Given, what's that capital F defined right there? I'm using that capital F for dynamics because the little f comes up here in stochastic approximation. But anyway, that's the evolution of a state-space model. And that dot product is the derivative of v of xt when xt is x and ut is u, okay? And so you're choosing the u to make the Lyapunov function go down as fast as possible. And if you can construct v in a clever way, you can get a stable algorithm. It won't minimize anything, but at least it'll get you to the top. And again, the sum of the total energy, potential and kinetic energy, is an example which works. You're trying to make that go downhill. So here's an example where you might introduce policy optimization methods where you have a parameterized family of value functions, and you try to find the Lyapunov function, I should say, and find the one that gives you the best performance. And the motivation for this is the DP equation. So in this model, the cost is identically 1. I'll get the notation going in a minute. We're just trying to minimize an integral from 0 to the time we reach the top. We're integrating 1 because we just care about the total time. And so if V were J star, we'd have an optimal policy. But then I showed you my J star. It sure isn't differentiable. It's really, the optimal control theory that was surveyed on Monday is really tough to apply here, when things aren't even differentiable. The value function is not. Okay. Anyway, now the Q function in some domains in this deterministic world is defined to be this sum. It's actually a terrible definition because it doesn't lead to good algorithms, but it's similar to the Q functions that we'll see later on. Estimating J star would be a mistake because once I estimate J star, what the hell do I do with it? I need a model, right? I need to differentiate it. I've got all this extra work to do. If I estimate the Q function, minimize it, I got my my policy, because the minimizer here is the optimal policy. Yeah. So that was Watkins' genius, back in the early 90s, was to estimate the Q function rather than the value function, which was done in TD learning. And we'll get to it in a minute, but there are two bits of magic in what Watkins did. Besides the obvious fact that here, if I know this, I don't need to know the model. That's beautiful. But there's other really important ideas as well. All right, get going. All right, so I just wanted to do a deterministic setting before we get into the stochastic stuff. So I've got X as my controlled Markov chain, and I've got an input U. I'm sorry I'm not calling it action, but I mean, if you look through all the early work, when I started, there were inputs, there weren't actions. I can't change, I apologize. I've got these conditional, I might not be in a finite state space, okay? So I have to talk about sets rather than points. So I'm looking at the probability of transitioning to a set A, given my current state X and my current input or action U, and all the prior history is this controlled transition kernel, so A could be a set. Now, when I get into, if I want to prove anything, typically I'll just stick to finite state spaces, but when we apply things, anything goes. And the theory doesn't need a finite state space. It really does not, except, with few exceptions. And unfortunately, it just makes my life easier to present this in the discounted cost framework. It's not my favorite setting. I prefer average cost for reasons I don't have time to explain, but I'll stick to this case of discounted cost, which is the most popular setting currently in RL, because then I've got this Q function here. So, so this is completely analogous to the Q function I showed you earlier in the deterministic setting. The only difference really is there gamma was 1, and it wasn't to infinity, it was until I reached a target set. And so I'm minimizing over all input sequences that are not clairvoyant, that are just adapted to the history of observations of this sum. So this is exactly the optimal value function you'd see in optimal control if you've taken an optimal control course, except instead of conditioning on the initial state, you condition on the initial state and the conditional input. Right? And that's the thing we'd like to learn. Yeah. And it really fits in with the standard theory because you can always say, well, I'm defining X and UN as a pair to be the state. Why not? It's a definition. So it really fits with the standard theory. Where the typical, if you have a control background, the typical setup is we condition only on the state, initial state. All right. Now this solves the Bellman equation. All right. Now let's stare at this for a minute. This infinite sum, I'm conditioning on U0 being U. I'm conditioning on X equals X. Those are frozen. So this very first term, when N equals 0, that's just deterministic. I can take it outside. And once I take that first term outside, I've got the minimum of a sum from 1 to infinity, right? And that's got a gamma up front. There's a gamma at the end. It's gamma 1, gamma 2, gamma 3. Pull that out. And what this is the cost to go. It's basically, wherever I end up, um, 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 the yeah, fortunately, I mean, I could derive it, but this whole thing, the sum from 1 to infinity, is just the same as where we started from, but it's a shame I used n. Damn, I hate myself. I mean, there's no mistake here, but I can see how confusing it might be. And I've used this slide so many times. Ignore the n here. That's 1, that's 0. All right, because that's what's really important, is that we're looking, when we look at this sum from 1 to infinity, it's like you're just thinking about, once I get from state x0 to x1, it's like I'm solving a new control problem from that random initial state. So I could replace that n by 20 and 20, or 0. Let's make it 0, because that's what's relevant. That I'm thinking of a new starting point x1, and from there I would minimize over all, in this case un plus 1s, but u1 if we take n equals 0. All right, so that's the Bellman equation. And that's the thing that, people come up with PDE solvers and all sorts of ugly things to try to solve. You get a model and then you try to solve this equation, and it's awful. The model being this horrible tensor function of u, x, for finite state space, a, I only have to do this for each a being a singleton. Get a model and try to solve that equation, it's a nightmare, And so I love the fact that, RL allows us to bypass system identification. Don't worry about trying to learn this model. Just go and try to directly learn this solution to this Bellman equation. It's poetry. It's absolutely poetry. As much as I am nervous about optimal control, avoiding system identification is just a wonderful goal. Now, what's funny is that people have learned that it can really help to do a bit of system identification to make Q-learning more efficient. That's beyond the scope of this lecture, but it's something to keep in mind. All right, so I need a name for this. This minimum here comes up so often. We need a symbol for it. So I'm just rewriting the equation I just showed you before, but I'm introducing some new notation. This Q lower bar just means a minimum over U. It's going to come up a lot. So whenever you see for today's lecture, whenever you see an underbar, it means I have a function of x and u and I'm minimizing over u. All right, so I've got this fixed point I'd like to solve. Now, just bear with me. Now you'll see why I put an n here instead of 0. I think here, there. So this equation, because of this conditional Markov property, is the same as this equation, where that Fn means I'm conditioning on all the observations up to time n. So every x0 and x1, x2 and x1, if I have some randomized policy, I don't know, anything that's observed up till time n is stuck in there. That equation and that equation are identical, means the same thing. Because here, you see I'm saying xn equals x, un equals x. I just plug in x equals xn and u equals un. These are identical. It's a definition of conditional expectation. This notation just means that. I mean, it's just, that's it. Yeah. And now you see I'm getting somewhere closer, because this here is the Bellman error. If this is not 0, if I stick in something besides Q star, this won't be 0. It's called the Bellman error. And so we'd like that Bellman error to be small. All right. I'm not going to know Q star. I'm going to have a family of approximations, basically defined by weights in a neural network, and I'd like Q star to be close to the thing that came out of the neural network. I don't know how to look at the distance between Q star and the Q out of the neural network because I don't know Q star. And so we use this Bellman error, when I replace Q star by Q from the neural network, we use that as a criteria for fit. And here it is. And I'm going to have to write this down and explain it. Okay, here's I'll say bounded. I don't really need bounded. I just need this expectation to make sense. All right. So saying the conditional expectation is 0 is the same as saying its dot product with anything that's a function of the observations. So this is what I mean. This is the history up to time n. All right. That is 0. And so what's done in Q-learning, the goal, even if it's not explicitly said anywhere almost, is to go through and design not one function. This is one function. There, it's a d-dimensional vector of random variables. And I'm asking for this property to hold, where that z is this temporal difference. Okay. What did I just do with mine? Look, where would it have gone? Behind the laptop. Oh, so who put it there? All right, do you see what I'm going here? Okay, so the Cn plus 1 is just the entire random monster there. Okay, and that's this thing here, which is called the temporal difference. All right, and this Q theta here, thetas could be again the weights in a neural network. I'm going to mainly look at linear families, but I'll talk about nonlinear as well. And that's my root finding problem. And I have to choose this vector here, this with care, but most importantly, it has to have this property. That's a function of the past observations. Now, it's this random vector is going to be d-dimensional if theta is of a dimension d, because I have d unknowns, so I need d constraints. All right? Yes. So this is what's called an eligibility vector in the work of Barta and Sutton, right? And in his work in the 80s, it was just taken to be a regression vector, and I've confirmed it was motivated by LMS, least mean squares algorithm, which was popular in the 80s. I suspected that for years, and I found it mentioned in one of these papers when I was looking for something else. So in one of the early 80s papers, it's basically stated that he's looking at an error times a regression vector. And that's what comes up in the LMS algorithm. Now LMS has some really good theory because of the fact that you really have a quadratic objective you're trying to minimize. Here we don't have that. So this is just a hack, There's no projection really of any form or anything like that, except for the projection theory that defines the conditional expectation. What this says is that the set of, if you assume everything is square integrable, it says that the conditional expectation this is commonly called z hat n plus 1 given n, is orthogonal to the subspace generated by functions of the observation. So there's that cute Hilbert space, interpretation there. But setting that equal to 0, damn it, there sure isn't anything obvious that that's going to solve. It's just a wild relaxation of the original goal. We're starting off with a constraint which is potentially infinite dimensional if xn lives in an infinite state space. Dimensional, but getting a basis for a large family of convex functions, it's pretty doable even in high dimensions. If you've got something nasty like the mountain car problem, good luck. I guess a neural network is a good choice. Um, in terms of the eligibility vector, I'd say the only thing anyone ever uses is that you take the Q function, you take its greatest vector theta, that's with backpropagation for a neural network, and you evaluate it at x and un, and that's it. And I jokingly call that Q0 learning in the book because it's a TD0, which looks just like it. And I'm sorry, but there's no motivation for this. A possible cure for cancer. I don't know, but I mean, semi-gradient descent doesn't have any meaning at all. Okay, it's just it's something to make us all feel better about a hack. And I'm sorry if you're listening, Rich. I love you. You've been an inspiration. I'm not kidding. I'm not making fun of anybody. I'm just saying, let's be real. This is uh, ingenious in many ways, but why it works is mind blowing. You know. Um, and the thing is that it's not like I trust everyone. People always report their successes and not their failures. But even personally, I've looked at the ugliest problems and looked at the stupidest bases and gotten really reasonable solutions using Q-learning, even though I can't explain why. I mean, I have a recent experiments with change detection where we just came up with absurdly simple 5-dimensional bases inspired by a few hacks. We run it, and almost every time we get the best policy in the class. We can identify the best policy in the class, and Q-learning gives it to us. And it frustrates me so much. Why does it work? It's amazing to me how well it works. And I don't know if I've seen any real failures, except with numerical instability, which we'll talk about. All right. All right. So there it is. There's Q-learning. So off-the-shelf Q-learning, this is what you'd find pretty much in Watkins' paper in the early 90s, where you take the temporal difference, you multiply it by this um, eligibility vector here. When I get rid of the thetas, it means I've just substituted theta equals theta n. Okay. I'm using this funky notation, which you wouldn't find in many books because I'm trying to, make everything match the stochastic approximation theory. And so that expectation with theta fixed is the F bar theta that appears there, which is associated with this stochastic approximation recursion. Okay. So this completely standard, this is not my stuff. This is Watkins 1982, I mean 1992, and what came later. All right. And then the policy you get, so remember again, the underbar means taking a minimum over U. Alternatively, if I define what's called the Q theta greedy policy, which is the arg minimum, I just substitute that in here, and that's also exactly the minimum over U. And then there's a choice of input. So almost all of the theory is you take the input to be IID. In Watkins' original paper, he only looked at what is called the tabular case, where you were not trying to approximate Q star, but you're trying to compute it exactly. And the theory there, UN is chosen independent, identically distributed, so you reach every state input pair, state action pair. That's not a good approach, but the theory becomes much simpler when you make that assumption. All right. Okay, so I'm just going to stick to this standard choice throughout, and also I'm going to stick to a linear function class for most of the talk presentation. Yeah, so what could possibly go wrong? Let's think about our rules. So I'm claiming this is stochastic approximation. It surely looks like it because I have an F bar of theta and I'm taking what's inside and plopping it down. So if you do a bit of pattern recognition, it's stochastic approximation, but it doesn't satisfy my rules. And let's look at that. Yeah. Oh yeah, well, that's right. In a second, I'm going to go through the rules, but this is the notation I'll use. I need something to define randomized policies. I'm going to have to talk about how you design a good input for exploration, besides something that's ID. If this does not depend on theta, then that's what I'm calling an oblivious policy, where the theory becomes much more elegant. Okay, so first of all, we get the nice Markov properties we'd like. So if you design a parameter-dependent randomized policy like that, then there's a problem with notation here. You'd have to design this. So for each theta, this would be a nice ergodic Markov chain. And all of you, let's just think about finite state spaces and action spaces. So it's concrete. So this triple for each fixed theta, don't run the algorithm, just fixed theta. This is a nice Markov chain with a nice steady state, unique invariant steady state. I mean, invariant measure and all that. And then I could define my F bar of theta like that. Everything works. What you get into is this thing Lipschitz continuous? And is this mean flow, associated with this vector field, is that globally asymptotically stable? Here, yes. For any of the function classes you care about, as long as you're in you have a finite action space, finite number of inputs, you get Lipschitz continuity. As I mentioned before, the minimum here, like for example, in the LQG problem, where the input space is continuous, this thing ends up being cubic in theta, and so you're dead. So you got to do some hack like you saw in the exercise. You need something to make it Lipschitz. Then there's a question of this thing being globally asymptotically stable. And basically the answer is no, except for in these very, very special cases, that I mentioned. All right. Now think about linear function approximation. So if you have linear function approximation, this is just writing everything down again. You have linear function approximation right there. It just means that there's a D basis functions, and Q theta is just a linear combination of those guys. And so, basically Q bar theta is just written down just like I wrote it. And then this eligibility vector now just becomes this regression vector, which is how it looked in Sutton's original paper, the very first 82 paper. And so you can see why that would help with analysis. And you can compute F bar of theta. You go and look at this, where's F? If you take the derivative, if you think of theta as a variable here, just forget the n. If I took the gradient with respect to theta, I would have two things I'd have to differentiate. The fact that this is a minimum is a function of theta becomes concave. So Q theta is linear in theta, but here, the underbar means you're taking the minimum of this over U. The minimum of the linear function is concave. Well, and if it's concave, it's going to be piecewise linear, typically for finite state space, finite action space. But at least it's got a subgradient defined everywhere. And the subgradient is easy to find. You you take the, see, the minus q there gives me the minus psi there. And when I differentiate this, the subgradient is I take psi and I evaluate it at this q gradient policy. So that's it. We've got this nice matrix. And then B, I'd say there's a B there. The B would be the mean of C times the eligibility vector, which I have there. And I'd have to write an expectation sub pi theta if I was using a theta dependent policy. The expectations in steady state, and that steady state could depend on theta if the policy goes a training. Yeah. Now, what goes wrong? I mean, yeah, the zeta, and then again is the regression vector. So something really happy happens with theta. We've got this the zeta, which is again this. I wish I hadn't done that way. I've got that times this with this psi transpose. So I've got an autocorrelation matrix. As long as my basis is full rank, meaning that the autocorrelation is full rank, the A matrix has this big negative component, which is really nice, a negative, a minus R, which is negative definite. But here's what causes the trouble. Even though you've got a contraction here, the gamma, the fact that you've shoved in this thing that has nothing to do with you properly, the product of that and that, its mean could be something huge and meaningless. And so you don't get that the Hessian is stable. I mean, you don't get A of theta for any of that in general. It just, for a general high ID input, you get garbage. And that's one explanation for these counterexamples. So the examples of Bard, which I'll show you, which shows that this thing is unstable. The mean flow blows up. The stochastic thing blows up. They're complex eigenvalues, which are in the right half plane, and you'll see the oscillations because of the complex eigenvalues. So it's really quite cool how predictive the deterministic dynamics are, and even just the linearization. For some strange reason, even though this depends on theta, the linearization of F bar is A of theta. That sounds like a contradiction. You might ask me, where's the product rule? It's because of the fact that, again, for an oblivious policy, you've got one part of A, which is this minus zeta and zeta in transpose, which doesn't depend on theta, that's fine. You've got another part that involves a minimum, and so the sensitivity is 0. Whenever the derivative exists, the sensitivity, one term disappears. So whenever the derivative of this exists, its derivative is, again, it's confusing, but it's a fact. Yeah, well, don't forget that a finite state space, finite action space, is easy to explain. Whenever this is differentiable, it means when you perturb theta, this policy doesn't change. So the sensitivity here is 0. So and so the derivative of this with respect to theta becomes 0. And so that's why you get that. All right. Now Watkins Q-learning. So if you go back to, again, Watkins' paper, he only looked at what's called the tabular case. In that case, you can get stability really nicely. It just pops out. This matrix does become Hertz. Everything becomes nice. And I will try to explain that. All right. So you've got a linear function class, so that this eligibility vector is exactly this regression vector. And the ith basis element is just an indicator function that x equals xi equals ui, where I've enumerated all state action pairs. So this is a depressing situation because there's a lot of state action pairs. And so I didn't want to compute Q star, I only wanted to approximate it. But that's what tabular Q learning is about. Here, again, we have stability, and there's a lot of special structure with finite end bounds that I said weren't possible. Here there are. There's some really special martingale structure that makes it possible. Outside of Watkins Q learning, that's not true. Just be aware of that. So yeah, one of the contributions of my student's thesis was showing that this asymptotic covariance with Watkins step size would be infinity. And that's why it's so soft. So basically, with that 1 over n step size, it was proposed in Watkins' algorithm, you get infinite asymptotic covariance at sigma theta. It's infinite in the sense that, I mean, what I mean by that is if I look at the error, I use tilde to indicate error. Okay? So this is a thing that's supposed to converge to something nice, this is what I'm saying goes to infinity if the discount factor is bigger than m, right? And so, it always does. And it doesn't, and when you hear infinite variance, you think, oh, big volatility. No, 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 no. You get, this is infinity because theta n, if it's stuck where it started, and just crawls towards theta star. And it's completely explained by the ODE. The only reason theta n is going slowly to theta star is because the ODE is going slowly to theta star. It's all about that, that tau n piece, basically. It's the fact that what I defined as tau n, it's something like the log of 1 minus gamma or something. I mean, times n. Maybe there's a constant there or something. You just take, wait, not there. I'm sorry, not, it's e to the, there we go. That's it. There's that A star there. So I look at the linearization of the mean flow. That's sort of the behavior, the linearization of the mean flow. A star has this horrible eigenvalue near 1 minus gamma. And so I get this 1 over n to 1 minus gamma for the ODE. And so I get this horrible bias. So that's what's causing. So that picture I showed you where Q learning output just showed a straight line and never moved, that's real. That was using Watkins' algorithm with a discount factor of 0.99, which is not big. But 0.99 discount factor is sort of like a finite horizon problem up to 100 or 200. That's not, large. So it's devastating. So you've got to fix it. Now, when Aditya, my student, was working on his thesis right there, we were both obsessed with 1 over n because of this historical literature on step sizes. And we didn't trust Paul Eckert-Erpert, even though we knew the work, we didn't trust it. We didn't trust it because we thought variance was everything. We really didn't get in our heads that bias was everything. Bias is what is killing Q learning. It's the dynamics, it's the nonlinear dynamics that's killing you. And you've got to think about both. Aditya's solution was to replace the standard step size in Watkins' algorithm by sticking a massive gain there. And guess what the gain was? 1 over 1 minus gamma. So it's 100 if gamma is 0.99. And so you get into this crazy oscillations, but at least that doesn't go to infinity. It goes to something reasonable. Yeah, as I said, so I think hopefully the next slide I explain why we have stability. the assumptions are in Watkins' paper, everything that followed, all the sample complexity bounds, everything that came later was assuming oblivious policy. So the input's ID, and you need this covariance matrix to be full rank. For this sort of ridiculous basis, this autocorrelation matrix is diagonal, and the elements are just, the probability of each state action pair. And so for this to be full rank, you need a pair process to be irreducible in the usual sense, that you visit every state action pair infinitely often, which is sad. I mean, really, we don't want to do that. With that. And that's a funny thing. So all of the sample complexity theory to date is based on an oblivious policy, yet everyone practitioner knows that's the last thing you should do for efficiency. So you're getting some sample complexity bounds, you're making assumptions so you can do the math. That those assumptions violate any principle for practitioners. We know that you've got to use, some epsilon greedy, some variant of epsilon greedy policies for efficiency. Okay, and again, this is just repeating what I just said, so again, if you do a million iterations starting at 0 and look at a histogram using Watkins off-the-shelf algorithm, you'll see something maybe it looks a little like a Gaussian bell curve. And if you didn't know the theory, you'd say, oh, wow, look at that. The median's there. I guess I've done it. The theta star is 75, But if you really know what's going on, you know it's actually 46.6. So that's why people say Q-linear is slow. It's just it's misuse of the theory. And then here's this step clause choice. I mean gain of a detail. We put, by the way, G over N X U means I count the N of XU means the number of times I visited the pair XU. Because that's what Watkins had in his algorithm. He didn't just have 1 over N, he had something else. And if you stick in 1 over minus gamma, you'll get something completely crazy. It's better than Watkins, but it's still awful. And later on, we learned we don't have to have such a high gain. And hopefully I can explain that. There's a growth story there. It's related to the spectral gap of the Markov chain, but you can do something more clever. I'll explain this later. Okay, so let me go a bit deeper. I mean, I told you I've got, basically this has an eigenvalue at 1 minus gamma. And it's very easy to explain. I mean, fairly easy. Okay. So this looks like it violates what I had before. Hold on, let me go back. Where's my A? So I need this. There. I'm just going to use some strange notation for you. So for a linear function class, I've got this zeta n, that's actually zeta n transpose. So that explains this first. And then I've got this zeta n again, which is psi n times this funky thing. And I'm just calling that psi underbar n plus 1 transpose. It depends on theta as well. And so this, Well, Watkins' algorithm, this thing here, remember size is a the basis element to get indicator functions of state action pairs. So these guys, the outer product here is just the diagonal matrix. And this mean here, the ith entry, is just the steady state probability of xi, ui, all i's. So the choice of step size after the fact, what it does is it replaces this ugly matrix by negative identity matrix. That's what actually needs to happen in Watkins' algorithm. But he doesn't really choose a step size of 1 over n. For each state action pair, his step size is how many times have I visited, it's 1 over how many times have I visited that state action pair. And so what it ends up doing is canceling out this and this getting minus y. So it really helps analysis. This is, okay, let's go back to that. So that's where you get a minus I here, because this thing gets canceled out. And what's really fun is that this weird outer product here turns out to be a matrix, which is a transition matrix, which depends on theta. It's basically the transition matrix, which takes an x and u to the next x, and then then the next u is just the greedy policy from that x. So you get this simple thing. And that, you can imagine, is a nice Hurwitz matrix. It's really not hard to see that. You know, the eigenvalues of this guy here are within a disk of radius gamma, and then here I've got a minus I, and so you've got, you know, you can write down the poles and zeros. And that's why that thing has T is a transition matrix. So can anybody give me an eigenvector of this? If T theta is a transition matrix? I know some of you can because it came up during lunch or something. Eigenvector? Lots of eigenvectors there. So you just need an eigenvector for a transition matrix. Some of you must have seen those. Well, there's a left eigenvector, which is the invariant, probably mass function for T theta, vector of ones. So if you look at A theta times a vector of ones, well, minus I, you get minus 1 plus gamma times 1. Okay, so that's the reason that Q-learning is nasty. It's got one eigenvalue, you know, which is very close to the origin, and the rest of them could be anywhere. It depends on this, not the spectral gap, it gets on something like the spectral gap. I think I've got a plot coming up. Hopefully, in a moment I have a plot of how of the eigenvalues for a typical Q function problem. Okay. All right. So, it's 43. One of the reasons this is an inherently ill-conditioned problem is over here. For finite state space, finite action space, I think this is equivalent, an equality as long as the discount factor is sufficiently large under conditions. What am I saying here? So this state action Q function is something here, and it depends on gamma, something that does not depend on gamma, okay? And then a constant here, which is the optimal average cost divided by 1 minus gamma. This is the relative value function for average cost optimal control. So I've got something that's bounded, you know, it's fixed in gamma, and it's just a constant that blows up. And so when you're trying to estimate the Q function, you're trying to estimate something in this nice living down here, plus a constant which is blowing up as gamma goes to 1. We don't give a damn about that constant. If we wanted to estimate it later, we could. We don't care about the constant because remember, the only reason we're trying to estimate the Q function is to get a policy. So if you throw away that constant, then you're set. One way to throw away the constant is to take the Q function. Oh, it's a different 8 star. I'm sorry. I shouldn't have used 8 star there. That's a different 8 star. Why don't I just change it? I'll make it lowercase. Oh, I'll call it G. Or something that's not the same as that. But if I take Q and subtract off its mean with respect to any probably mass function at all, I kill off that constant, because the mean of a constant is itself. So I kill it off. So you can come up with an algorithm that estimates this function rather than that function, and everything disappears. So this eigenvalue ends up getting moved in, and you don't have the problems at all. So a warning to all of you: when you see error bounds of that order, when you see something like this, scream. Because when you're saying your error bound is something small over 1 minus gamma, gamma is close to 1. That's not a good bound, no matter what anybody says. It's basically they're saying that the estimate of that constant isn't good. Just get rid of the constant. So you'll see bounds like this in all of the literature in Q-learning. It's not a good bound. You've got to change your objective. It's something like that we care about. So let's up. And I'll show you what happens then. Oh yeah, let's see. Oh yeah. Now, there's an alternative which I like better, I think. Okay. You take the Q function, instead of subtracting a constant, you subtract subtract its minimum. So 8 star here is the minimum of Q star over all U. All right. And these both have the constant in them. The constants get subtracted. I think this might be better than the previous approach. There's not theory yet for this. So here, there's a fairly nice theory for doing this. Here, I think there will be a complete theory. So I think you should consider both. But writing Q-learning without some sort of modification, you're going to get problems if your discount factor is close to 1. I forgot I had something on this. You can go through this. Let me see. Oh, no, this is too much. We don't have time for this. We don't have time for this. We really don't. Forget it. Yeah. This V star, well, no, I mean, you see, the thing is that if you go through and you look at this, you'll get exactly the same equation. So if you solve this, you would just solve, there'd be no difference between Q-learning. But if you choose your basis, look at a linear function class. If you choose the basis function so it's compatible with this objective, then you end up estimating the advantage function rather than the Q function. So it's the same algorithm, but just with a careful choice of basis. And where is it? Right there. So you choose a basis, which was the original basis used for Q-learning, but subtract off something, which is perhaps, this depends on theta, the current greedy policy. And the thing is that subtracting a function of x doesn't change anything in terms of, to get my policy, I'm just going to minimize every u. And so I get numerical stability properties, but there's still some questions. So here's a research topic. Trying to think about the best design for this. Oh yeah. So the theory for fixed policy algorithms is complete. That's all solved ages ago. It's all well thought out. It's when you apply this to Q-learning, it's still, there's some subtleties, I think. Maybe not. All right. Okay, so here I've got some numerics I can show you. So I've got, and a warning. So my student and I developed all this in the tabular case where it's so beautiful, it's amazing. You can just see how that eigenvalue gets moved. You can compute where it gets moved. It's completely perfect. When you're looking at a linear function class or a neural network, it's not quite as elegant. And the reason for that is we don't know this eigenvector, we don't know which is the worst eigenvector, even though we know there's a bad one. Again, I think it comes down to choice of basis selection. You choose the right basis, it might be completely trivial to know what the worst eigenvector is, and then there's a good theory. I'm presenting stuff that's quite new, which is, so there's lots of holes here. So this is the thing that we want to estimate, where mu is a well, mu would be probably a mass function here. Oh, Jesus, something scrambled here, but let's not worry about it. Anyway, forget this. I'm going to introduce another probably mass function here and try to solve this equation. And I feel there might be a typo in the slide, so I'm getting nervous, but it's okay. And then, yeah, that's not, there is actually. This is all correct, but I have a problem because I want a probability mass function. Yeah, nu, I've got this backwards. So nu is just a positive measure. It doesn't sum to 1, okay? Because I definitely need a probability mass function there, not for nu. Okay, so I take some nu, which is just positive, and if I solve this equation, I've really solved the equation I'm interested in with that 8 star if I take this mu. So the mass of nu has to be 1 minus gamma over delta. It's not a probability mass function. Anyway, and so yeah, then you just have the same algorithm and you have this temporal difference. It's very, very simple modification. And you want this to be simple to compute. So take nu to have its support on one pair, this one state action pair. So it's not really the mean under nu, it's just evaluation, right? And then do the same thing, we're gonna stick in a matrix gain, which turns out to just be that. This is my estimate of the, I'm just trying to invert this guy. Watkins' algorithm is just sticking a matrix gain really to knock that out. And so here's what I said is really pretty. You had this matrix here. Somehow I wrote p theta star because that's what t theta turns into. Oh, no, it's not. Anyway, forget that. That's t theta star. It's not p theta star. This would be the p for the joint process. X and U process is a Markov chain. Caillou, make a note for me. That's an important typo on page 13. That p should be a t, a theta star, blah, blah, blah. But so this thing had an eigenvalue at 1 minus gamma. I'm subtracting off a rank 1 matrix, and that 1 is the same as that eigenvector 1 there. And I end up shifting the eigenvalue by amount delta. And you can see that if I take delta equals gamma, I'm taking that horrible eigenvalue at -1 minus gamma, and I'm shifting it to -1. So if you do tabular Q-learning, this is the way to go. And if you're doing binning, this is the way to go. Because tabular Q-learning and binning have the same analysis, the same issues, everything's the same. And it would be crazy not to do this. Absolutely crazy. And especially since it's an invertible operation. You learn the same thing. Where is it? Yeah, if I know H, I know Q, because I've got this mapping between everything. So it just makes no sense not to do this if you're embedding to the tabular case. All right. Now, if we're not in the tabular case, we're going to get the A star minus some strange outer product, where this psi bar is the mean of psi in steady state with the straining pulse we're using. And this other guy is the mean under nu that we chose. And we just don't know as much about what's going on there. Okay. Oh yeah, oh yeah, what is there? Oh God, I need a plot for this. I want you to get a feeling for this because there's a message here that needs to be revealed. Okay. So I told you the eigenvalues for Watkins' algorithm, there's one that's really close to the origin. That's in typical applications, that'll be 0.01, maybe 0.001. And then there's a bunch of other eigenvalues. They come in complex conjugate pairs, something like that. As I said, there's a typo that should be gamma times t theta star. It's a transition matrix for the joint process XU under the optimal policy. That's what that is. So what happens is this improvement I'm talking about, all the eigenvalues satisfy this property. And I only care about the real parts of this matrix, which should be t theta and not p theta, whatever. And it turns out it's the real part that matters. So well, anyway, let's go back to t theta. So there's an eigenvalue here at 1. And that's something that we could ignore. We'll look at the real parts of the eigenvalues of that matrix. All right. So, so for example, let me give you an example. Suppose there were eigenvalues there and there. Would that bother you? Suppose there's an eigenvalue right on the unit circle. Would that bother you? No, it's not the spectral gap. What gives you fast convergence is making sure the eigenvalues are far to the left of 1. So this, with all the eigenvalues here, even though there's no spectral gap, it's not ergodic. It's the best. It's a great scenario. In fact, taking these eigenvalues and sticking them there at -1 would be better because we would maximize, we would, yeah, I mean, that rho star become negative, we'd make things much faster. We'd have better performance. So it's really interesting. The spectral gap is not the issue of these things. You don't want fast mixing. You do not want fast mixing. You would prefer oscillatory behavior. Which is what you'd get again if all the eigenvalues were complex for this. I mean, -1. It would mean you were completely oscillatory. And you could imagine that. You have a process which is going up, down, and 1, -1, 1, -1, 1, -1. You average that, the law of large numbers converges much faster than something very ergodic. That's what's going on here. We're doing averaging. So this intuition about spectral gap really falls apart when we're talking about these recursive algorithms. And this is a really good example of it. All right. And again, this is pollution from a few years ago when we were trying to fix a one over n step size. It's true that if you use this step size, you will, with the alpha in there, and I've taken this matrix outside, you will get a finite asymptotic variance, which is what Aditya proposed. At first, in his first paper, we had rho star equals 1 for the standard Watkins algorithm. We could improve that here, but don't forget the rules. Don't do that. Use what I proposed before, like n to the minus rho, rho is strictly less than 1, and average, you'll do much, much better. Aditya and I were trying to do two things at once. We're trying to deal with the nonlinear dynamics and the transients, and also deal with the stochastic variability. Those are separate issues. You do the relative Q-learning thing to deal with these horrible dynamics, an eigenvalue that's near the origin, But then the stochastic stuff is trivial. You just crank up the gain and average. Done. Is that clear? This is such a good example. He's gone. It's such a good example of how you design dynamics to get what you want. I want to get real nice, nice stability. I want really well-conditioned mean flow. The stochastic part is just blah, 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 right there. Nothing to it. Okay. Now I'm going to not do so much commentary. We'll just move this fast. I'm not going to say much about this. I'm going to say that for linear Q-learning, you can have stability for free. If you have a linear function class, and as long as you choose your policy as something like epsilon greedy, like I choose my input to be pretending that my Q function is perfect with high probability, and alternatively, just do something crazy. You just uniformly at random, check my input. You can show stability, and how you show it is by showing that, for example, we prove that this thing is Hurwitz, and you also can construct a Lyapunov function for the mean flow and prove stability. That's very new. Unfortunately, if you use like what's called a Gibbs policy, where you choose probabilistically according to this rule, where z here is a normalizing factor, that violates the Lipschitz condition, so you have to modify it. But I don't have time for that. Let's kill it. Kill it. Because I wanted to show you some pretty pictures. But I need this, too bad. We're not gonna be able to talk about ZAP. We're out of time, 3:20, only have 10 minutes. We have to talk about this because it's in your homework. So this is a modification of Bard's famous example in which you have this state here where you get $1 million. Every time you hit enter, you get $1 million, or you're over in these states and you get fined. And anytime you want, if you're at state 6, you can move to state 7 and stay there forever. So we know the optimal policy: go to state 7 and live there forever. But he showed a different context that a poor choice of training can lead to instability. Okay, so Gordon had one variant of this for Q-learning, and I cooked up my own because Gordon didn't really work for me, just for what my purpose is. And in choosing the sort of the training input that Bard proposed, first of all, you can see that if I look at the linearization, I get these eigenvalues on the right-hand side, at theta star, and see how they're complex. So then the right-hand side, they're also very complex. And you see the parameter estimates oscillating, and that the natural frequency there is consistent with the frequency up there. So we see it learning a lot from the ODE and just the linearization, even though it's not a linear system. Um, and well, these are actually TD learning, but it's the same thing. Um, so and then what happens when you introduce this epsilon greedy policy here? And I can't go through it, but that's a smooth approximation to epsilon greedy, and that's just some uniform nonsense, some noise. Depending on gamma, you have to take smaller values of epsilon. And for gamma equals 0.9 or 0.95, you can get away with, I don't know, 0.3 or something. And the eigenvalue analysis says there's some hope. But when gamma equals 0.99, believe it or not, that's negative. You can't see it in this plot. And I didn't use relative Q learning. Okay, so if I used relative Q learning, you wouldn't see such dependency on gamma in this example. They would all be very similar. This is an example of the evolution of Q theta n valued at one, if the optimal state action pair converges to the value -2 rapidly. The reward was 2. I convert to cost, so it's -2. And with 0.99, it goes to infinity. Again, if I'd used relative Q learning, even though there was no theory in this paper, it wouldn't see a difference. Yeah. So now here's a problem with relative Q learning. I'm saying you wouldn't see such dependency on gamma, but it's not as rosy as in the tabular setting. Let's stare at this. So here are the eigenvalues with a particular example, this is with this this epsilon greedy sort of training. I've got this eigenvalue really close to 0. I'd like to move it. I'll use relative Q learning, and it kind of works and it kind of doesn't. So I have a nu I have to choose somewhere. If I choose my nu to be the point mass at 7, 0, it's hard to tell, but these are different. But the nasty eigenvalue here doesn't move. And it turns out that I'm just missing the problem eigenvector completely. So it doesn't help. It doesn't help the dynamics. Numerically, we found it helped a bit in experiments, but we still have that troubling thing. Now, it's not hard to find the worst eigenvector for A star and choose nu accordingly. And that nu turns out to be a point mass at state 5 in action 1. And I guess it's so symmetric that state 6, 4, 3, 2, 1, any of them would get the same result. You probably have no difference at all. And this eigenvector moves in considerably, considering how close that is to 0. This guy gets swung in, which looks a little bit scary. But I know it's going to be Hurwitz. Well, I have to be careful. I guess this could possibly go into the right half plane because this is again fairly new. There's not a lot of theory for this. So you'll play around with this. Maybe you'll have a better idea. I wish that I had you code advantage Q learning instead of relative, because I think that would probably be more robust than this. Okay, just keep that in mind. But yeah, so theory is lacking. And so yeah, I'm just repeating what I just said. So I have a feeling this could give better results. But it's not, you can't pick up a book and find this. I gave you an algorithm. For TD learning, it's brilliant. For Q learning, with that sort of policy, I know there could be theory by Christmas, but it hasn't been published yet. And I don't have time. So if I had time, I would have showed you how beautifully it all works, and how you look at all the AI gym experiments, and it's insanely reliable. It always gives you good results, as long as you take the complexity of your neural network large enough. And if you click that, you can get the code. and you can play around with it. And I would talk about ZAP 0 and how you can go through and create this crazy 3D dimensional equation, which is also universally stabilizable and can easily be translated to get a stochastic approximation algorithm. And you will note there are no matrix inverses. There's just A times the product there, but there's no matrix inverses. This can be proven to work. Where's LT? Yeah, where this LT is just this thing here. But empirically, it sucks. I mean, at least for ill-conditioned problems. Empirically, you just get these massive excursions and come back down. So it's another fun area of research, is how can you design dynamics better here to avoid a matrix inverse and get some nice robust properties. So here's a hack that I can prove works, but again, the transients are too ugly to use it. I would not recommend this. So anyway, okay, so that's it. Conclusions. I think the biggest maybe surprise that this field doesn't exist yet. The empirical success is amazing, but the theory predicting success is so small. It's amazing. And that's my favorite question, is why does it work so well in practice? And yeah, and I hope you understand that this nonlinear dynamics is one of the big curses. It's not just like variance and dimension. It's the fact that you can have an eigenvalue at 1 minus gamma, as simple as that. And there's other things like that. Unfortunately, I didn't get to talk about ZAP, but it's magic. I mean, I always use it because my problems have dimension of less than 100. So why not? I mean, throwing in a matrix inverse is nothing. And again, this biggest research question on Earth, you'll get the Turing Prize if you can explain why solving the projected Bellman equation is a worthwhile pursuit. We know it is empirically. We don't have the theory to say why. It's something else. And the rest of this I can't really talk about. So I'll just close there. So I hope this was useful. It was it was more dense than I even thought. I hope you'll be encouraged to go over the slides again and pick up what you missed. Any questions? No? Okay, you can applaud. Well, thank you. Hmm.